When we continue still table, image from set page 270 for the reference. So the face diagram has the following appearance. This is the common phase diagram, solid, steam, and liquid. Pure water may coexist as liquid and liquid only at temperature pressure pairs that follow the curve. At point above the VNE curve, but to the right of the solid liquid equilibrium curve, water is the liquid. A point on the VLE curve. So VLE curve is referring to this line. Water may be saturated, may be saturated liquid or saturated steam, or a mixture of both. If it's fall under the line, okay. But this is for water. For methanol or other type of solution, the phase again different. So for this is for water, should fall under the line. So it can be both mixture of liquid and steam. Below the curve, so superheated steam. Further, table U5 or P7 to delete B. Page 642. So for the table B5, it's regulated as temperature, but it's limited to 100 degrees C, 102 degrees C. Table B6, yes, pressure. So the highest pressure is 221 down. Replacement for the critical pressure. Then table B7 is for the superheated. So table B5, table B6 have a different type of form, water, steam, evaporation. But for table B7, it's a superheated steam. Determine the vapor pressure, specific internal energy, and specific enthalpy of saturated steam at 133.5 degrees C. So for this case, you need to refer to table B5. Right. But table B5, the highest it can cross is 102 degrees. So since it's not available in table B5, don't do extrapolation. You can refer to table B6. So table B6, you refer to the second column. for the temperature. 133.5 is 3 bar. This is for the steam. So we have volumetric flow rate, thermal energy, specific energy, then enthalpy. So for the vapor pressure, it's 3 bar to dissolve, 3 bar. For the specific flow rate, this is for the steam, so it's 600 per kilogram. Question double opinion. It should be 5. Then we have specific internal energy, positive is 2.43. The last one is specific enthalpy. Steam is 2724.7. So we have enthalpy, the water, evaporation, and steam. This is the question asking for saturated steam cells. And then this steam. Show that the water at 400 degrees C and 10 bar is superheated steam and determine its specific volume, specific methodology, specific enthalpy relative to liquid water at the triple point at which to be. So since it's asking about superheated steam, so we will directly go to table B7. So for table B7, says this 10 degrees C, so 10 bar, 10 bar. So for 10 bar, if you refer to table B7, the first page 630, under the row 10 bar, the temperature is until 350, but the question asking 450. So you need to refer to the next page. 10 bar, and you see is the second column. So second column HUV. So H3264 2958 30307. TDP is the dew point at 179.9. So that is how you use a table V7. Show that U and H for superheated steam depend strongly on temperature and relatively slight on pressure. So still table 7. So let's say the same pressure and C for the 400 degrees C, the U, sorry, the specific enthalpy U, specific internal energy U, specific enthalpy H. You see the changes with increment 50 degrees C. Strip set. Now consider at 10 bar, both at 400 degrees C and degrees C, as check for the 20 bar. You see the equipment is in 20, what so reducing by 9, changes by 1%. So meaning it strongly depends on temperature rather than pressure. Example, steam at 10 bar absolute with 180 degrees C of superheat. So superheated steam is what table B7. This factor a turbine at the rate of 2000 kilojoule per hour. The turbine operation is identical. The fuel is saturated steam at 1 bar. Calculate the work output of the turbine in kilowatts, neglecting changes in kinetic and potential energy. The energy needed for this steady state system is WS. WS referred to shaft work equal to delta H is enthalpy. M is mass flow rate, so the dot here refers to the rate. It's over time. Then H out minus H in this is specific enthalpy. Specific enthalpy normally it's over kg or mass, can be something else. Why was the heat inlet steam table P7 indicated at 10 bar is saturated at 180 degrees C, so that the inlet steam temperature is 180 plus 190, 370 degrees C. Everything in the same table. So H in 300, sorry, H in at 10 bar or 317, because if we refer to table B7, the temperature is increment of 50. See, 300, 350, 400, 450. Then the specific enthalpy is 3201 kJ. Next is table B7 for outlet steam from either table B6 or B7. You can find that enthalpy of saturated steam at 1 bar is H out 1 bar. So since this is a saturated steam, not a superheated steam, so you can either use both, but better use table B6. So you get H out 1 bar saturated to 675 kilojoule per kilogram. Energy balance. So W is shuffle delta H. So delta H is referred to this equation. Go to this equation. H out to 675 minus 3201 in unit conversion, then we get negative 292 kilojoule per second to negative 292 kilowatt. The turbine does deliver 292 kg of work to its surroundings. So the negative reflected it either goes to the system or system. Exercise still at 260 and 7 bar reps is expanded through a muscle to 204 bar. So inlet is 260, then the outlet is 200. So since 260 is not in the saturated uh, table BC. So you need to refer to superheated steam table B7. Then outlet is 200 degrees C and 4 bar. Negative is transfer from the nozzle to its surrounding. Also velocity of the steam is negligible. The specific copy of steam is 974 at 16 degrees C and 7 bar. Here's semua ada. And at 60 kilojoule per kilogram at 200 is used. Open system able to calculate the exit steam velocity. Refer back to the equation. Right there, velocity. So this is an open system measurement. So you find the open system measurement equation in which 7366 equation 7.4-15. So in this equation, the EQ and gravity 2 minus U1 square. In this case, U1 for inlet is 0. So the approach velocity of the steam is negligible. then okay equal to m over 2 dapat this. We need to use this equation. Transfer dash 15. Before you get 7 dash 15, open system equivalent. There's a set of the derivation. From the derivation, you can identify which term that have velocity. So in this case, it's kinetic energy. Next is energy balance procedure. When labeling the flowchart, include all the information you will need to determine the specific enthalpy of each stream component, including non-temperature and pressure. Okay, show state phases of procession when they are not obvious. Do not simply write H2O, but because the phases of the process radial, there's it they have different value for enthalpy, internal energy. So I did with the form of phases is equivalent on one component process. Two streams of water are mixed to form the feed to a boiler. Process data as follows: feed stream 1 is 50 kg per minute at 30 degrees C, right? Second stream 175 kg per minute. You see the form here with it. It's 65 degrees C. Steam emerged from the boiler through 6 centimeter ID pipe. Calculate the required heat input to the boiler in kilojoule per minute. If the emerging steam is saturated at boiler pressure, neglect the kinetic energies of the liquid input stream. So the outlet is 295 kg per minute. In this case, they wanted them to different since this is a boiler. Pressure rises to 17 bar. Outlet. It's saturated steam. Step one, first step in solving this what the problem is to the if possible the flow rate or stream component. In this case, it is a trivial method to write and solve a mass balance on water to determine that the flow rate of the emerging steam is 295 kg per minute. So the 295 kg per minute is based on mass balance. This one. We add this up, then we get the 295. Okay. Next, determine the specific enthalpy of each stream component. Table B5 and B6 were used to determine sorry, enthalpy for liquid water at 30 degrees C and 65 degrees C. So this one is table B5 and B6. Since this is below 100 degrees C, so you can use table B5 easier. But need to make sure which one is the fault. Water, steam. Alright. So the latter entry in the table also furnished the topic of the saturated steam corresponding to this pressure 200 for degrees C. This is for the outlet. So for the outlet, we use table B. This is not that the entries for liquid water correspond to pressure that may or may not equal the actual pressure of the inlet stream, which we do not know. We assume, however, that the enthalpy of liquid water is in the drop pressure and use the tablet range. Step 3. The final step is to write the appropriate form of the energy balance. So it for the desired quantity. So since this is an open process system, so we use 7.4-15. There are no moving part. This is just a boiler. So W is 0. Generally, so for the potential energy, assume to be 0 unless there are displacement inside the volume in the boiler. So the term left is heat equal to enthalpy plus kinetic energy. Then we do the calculation. For equation 7.4-14a, the hash equal to MIHI, that one is for the outlet. Okay. Let's go to inlet. So 295 kg per minute multiply with the specific enthalpy we calculated earlier, we find it earlier, minus the inlet. There are two inlets, 1 kg multiply with the specific enthalpy. Where do you get the specific enthalpy from? Table B5 or B6. Then you get delta H equal to from table B6, the specific volume of saturated steam at 17 bar with 166 cube. 11. And the cross-sectional area of the 6 centimeter ID pipe is in this equation. Equal to pi r squared. And we get the cross-sectional area. The steam velocity is U equal to V, the volumetric flow rate, divided by area. We get the velocity. Here, 295. This is the outlet. Steam conversion. This is the steam density. Density of steam. Steam density. Check. Oh, it's depend on the steam density. Oh, no. So 0.116. I thought this is a density of steam. It's specific volume. So the specific volume you can find it out. It will be probably 5 or be 6. It will be 6. Yes. Oh, this is the area. So you get U equal to 202 meter per second. Then since the kinetic energy of the inlet stream, I'll assume negligible. Oh, since the kinetic energies of the inlet stream are assumed negligible, so EK is equal outlet stream. Okay. Negligible. Oh yes, neglect the kinetic energy of the liquid inlet stream. Then we get delta EK is 6.2 kg per minute. It's the kinetic energy. But the question asks you about calculate the resolution. Okay, Q So Q is equal to delta H plus delta EK. So delta H is this one, 0.61 plus delta EK is 6.03, this one. So get 767, 7.67 10, 10 to the power of 5 kilojoule per. So as of that, definite energy change is only a small fraction, roughly 0.8% of the total energy requirement for the process. This is a typical result. It is common to neglect kinetic and potential energy changes, at least as a first approximation. Relative to enthalpy changes for processes that involve phase changes, chemical reaction, or large temperature changes. Exercise. Mm, look. A turbine discharges 200 kg per hour of saturated steam at 10 bar absolute. This is desired to generate steam at 250 degrees C and 10 bar by mixing the turbine discharge with a second stream of superheated steam at 300 degrees C and 10 bar. If 300 kg per hour of the product steam is to be generated, how much heat must be added to function? So this is Q. To find Q. So if we back to this previous example, go back to the previous example, do the step. The first step is to determine the rate of all stream components. So I suggest draw the block diagram. So in this case, if the find this chat 100 kg, decided to do check at 250. There are okay. See, there are two inlet here. So the first inlet is 200 kg per hour of saturated steam at 10 bar. This is from the previous turbine. It's just this amount. Then the second stream is 300 degrees C and 10 bar. One is the second inlet. So the output is 250 10 bar. So you do the explainer to find the second stream, second inlet. Because if you refer to the question E, the product steam generated is 300 kg per hour. Ada. Okay. Since once we get the mm, mass balance, we go second step. So the second step required you to refer to table B5, B6, B7. Yeah. So that one, why you need to identify the enthalpy for each of the stream inlet outlet to inlet one outlet, so three. Then what else? The final step is to write the appropriate form of energy balance and solve it for the desired quantity. So write the 7.4-15 equation for the open process system. Identify which term is 0. So since this is turbine, so delta EP is 0. See, potential energy. Next is the check what for 0 is WS. WS pun, so WS is so uh, oh, wait. So for the question A, so the final form is Q equal to delta H. Since the question there are no velocity, you see, meaning you can assume there are no negligible kinetic energy is negligible, no 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 moving parts in sharp mode. There are no what else? Delta EK. So the remaining term is Q equal to delta H. So delta H in this case referred to question 7.4-14A, which is delta H equal to MHI, that one for inlet, sorry, outlet minus MIHI for inlet. So M referred to the flow rate that we do the mass balance. Then the H is based on the step 2, where we determine the enthalpy for each of the stream. Yeah, that one is for the Q. For P, if instead the mixing is carried out adiabatically, at what rate is the product steam generated? So you need to understand what does the adiabatic mean. What you can refer to which let's 61. That's so for the term, the specific term identity, the definition. If a system and its surrounding are at the same temperature, or the system is perfectly insulated, the process is then terminated. So meaning the Q is zero. Right? So the Q is zero. So delta H is zero. So the delta H is zero, then you can calculate for the n. How you calculate for the n? You refer to equation 7.4 H plus E and then into this plus D right? If the H in I H I was a constant, if this sufficiently knows in I H I, we find the M I for the picture. All right. Energy dependent on two components. Liquid stream, this is an example. A liquid stream containing 61% ethane and 40% n-butane. To be heated from 150 Kelvin to 200 Kelvin at a pressure of 1 megapascal. Calculate the required heat input per kilomole of the mixture, neglecting potential and kinetic energy using tabulated enthalpy data for ethane and butane. For ethane and butane, assume that mixture component is titles of the pure species to reducing the picture. So the piece of butane with 150 Kelvin and 1 APA and 200 Kelvin. Oh, given on page 2-222. So the first two refer to the volume. The second 232 is the page number for that volume. It's how you write as how you identify page number in very chemical engineers handbook. In terms of ethane, so meaning this value enthalpy for the butane, enthalpy for the ethane is not available in your appendix for this book. So in appendix A, B, or any appendix, the enthalpy values are shown in the energy banner. Mol, decay, Kelvin, kappa, system population. Based on this, so 1 kilomole per second here is a reference. Otherwise, you don't know how much is 61%, 10, 14%, and 10. So in this case, the reference is 1 kilomole, or they assume the fluid to be 1 kilomole per second. So since this is a heater, so ideally, this will come in is equal to the outlet. No, I think that's since that okay. So straight to the equation, equation for the open process system. Says now, okay. So the term left with Q equals to delta H. It's the what is already said. Why there are no potential energy kinetic sharp inside? Since the potential again assume agent case behavior, we may set the enthalpies of each string equal to the sum of the individual component enthalpies on the right. equal to delta H equal to this equation. So this equation here we refer to 74 dash 14 EU. So since they identify already this value for the enthalpy, not really identify it's given. Since you don't have to put the Perry handbook. So this is from the Perry handbook, the enthalpy of the outlet and the inlet. But for the flow rate, the molar flow rate, that one is from the question based on 1 kilomole per second fitted, or they call it basis of reference. Then calculate, we get 4460 kilojoule per kilomole to heat specific specific heat. Sorry, kilojule. So it's heat. Another example, superheated steam at 300 degrees C and 180 atmosphere is to prevent a heat exchanger. It is produced by mixing an available stream of saturated steam at 180 and discharge from a turbine at a rate of 1150 kg per hour with just taken stream of saturated steam. Or at 400 degrees C, the mixing may be considered diabatic. Calculate amount of superheated steam at 300 degrees C produced and required volumetric flow rate of the 400 degrees C steam. So first of all, you need to draw the log diagram. So this is a mixer. The As on the name that implies. So a mixer must be mixing something. So to mix something, you need at least two stream for the inlet. So for this case, the first one is the turbine discharge 1150 kg per hour in vapor form, 180 m saturated 100 degrees C. The hash is 26. Okay. Next is M1. So M1 is the second stream. That one is what we want to do. So and yes. So from the mixer, need to find another one M and 2 for rate for the outlet. The one is kg H2O per hour in vapor form as well. Then 300 degrees C, the picture 180 M. The specific enthalpy of the two feed stream and the product stream obtained from the steam table and are shown below on chart. Okay, there are two unknown quantity in this case. Ada one material balance. The material energy balance must be probably solved simultaneously in determining the two flow rate. So in this case, the mass balance for water is 1,150 plus 1 is equal to N2. Next is the energy balance. Start with the equation for open system. Identify which term is 0. This case Q is equal to 0 because the process is identity. Unknown moving part, then the is equal to 0. And data EK, data EP is 0. That is based on the assumption. Then the final term is delta H equal to delta H equal to MHI minus N1HI. That 7.4 dash 14E. So this equation is equal to 0 because Q is 0. So all of the term is 0 except for H. Down. Next is solve the equation. So 1150 2676. One is for the this equation. So you have two inlet, one outlet. So this is the outlet. One. Is it the outlet or inlet? Oh, the inlet. 1150 2676. Plus M1. So M1 is the inlet as well. So the inlet term is negative, but you move it to the right hand side. It's the positive. The M2 is 1 equal to the outlet. Let's solve this equation. The first equation is from the mass balance equation from the energy balance. You get the M1. But the question didn't stop there. It's asking for volumetric flow rate. So for the volumetric flow rate from table B7, the specific volume of steel at 400 degrees C and 1 atm is 2.11 meter cube per kilogram. The volumetric of this stream is therefore is therefore 2240 per kg per hour. This one, this value. Multiply with the V. So this volumetric flow rate is coming from table B7 at 400. Why you need table B7? Because of the uh, table B6 is till 221, the critical temperature. Then you get 6980 meter cube per hour. So if the specific volume data is not available, if you don't have this table of the segment, you can also use the gas equation of state. The gas equation of state is PV equal to nRT. Exercise. So exercise, can try this one. You need to find Q. So first thing you need to do is draw the block diagram. Then do the mass balance if required. After mass balance, you do the find the enthalpy. Since this is propane and butane is not available in the appendix, you can refer to that table there to write the full equation 7.4-15, which is open process system. Identify which term is zero. Yeah. In this case, this type of equation, you can know it. Delta EP, delta EK is obviously zero. There are no WS here. Shuffle zero, so the final term is Q equals to delta H. So delta H is refer back to the 2.4 dash protein A, M1 MI, so summation of outlet HI, summation of outlet HI. From there you get the stuck in the value, get the Q. Mechanical energy balance. So mechanical energy balance, another important class of operation is one for which the opposite is true. If no and an internal energy changes, the second view important to kinetic and potential energy changes and shuffle. Most of this operation involve the flow of fluid to from and with tanks, reservoir, and process unit. Counting for energy flow in such processes is most commonly done with mechanical energy balance. 7.7-2, this is another equation. So this equation is specific for mechanical energy balance. So far you learn about closed system and open system. Now is mechanical energy balance. It's different. The term is different. So this is valid for steady state flow of incompressible fluid, water, obviously. The method of estimating friction loss from flow through straight pipe orifice nozzle elbow, that one referred to the F here. It's not available in the appendix. Can refer to very careful in your handbook, but it will not be discussed in this text. If it's given, then you need to count it in. If the value of F is given, then you just use. A simplified form of recurring unit is obtained for frictionless processes. So meaning F is equal to 0. In which no shuffle is performed, then equation 7.7-2 uh, will be simplified to 7.7-3. So 7.7-3 is Bernoulli equation. So continue next class. Thank you.